Hi everyone. Today's lecture addresses a fundamental issue in contemporary architecture: the relationship between material selection, environmental sustainability, and disaster resilience. In the context of urban morphology and hazard exposure, material systems are not passive construction elements. They actively determine how a building performs structurally, environmentally, and socially, especially under extreme conditions such as earthquakes, floods, or post-disaster reconstruction scenarios. We are living in a period where climate change, rapid urbanization, and increasing disaster frequency require architects to move beyond aesthetic and cost-based decisions. Materials must now be evaluated based on structural behavior, carbon impact, durability, recyclability, and adaptability. In this lecture, we will specifically focus on wood-based panel materials and engineered wood systems. We will examine how these materials contribute to sustainability through recycling, how they perform structurally in seismic regions, and how hybrid systems combining wood, concrete, and steel offer improved performance in disaster-prone areas. The ultimate goal of today's lecture is to develop performance-based material thinking. In this session, we will move through several interconnected themes. First, we will discuss waste recycling and its contribution to sustainability. This includes how industrial wood waste is transformed into construction materials and how this reduces pressure on natural forests. Next, we will analyze wood-based panel materials, including particle board, MDF, OSB, plywood, blockboard, and laminated wood, from both environmental and structural perspectives. We will then evaluate how these materials perform in post-disaster temporary housing systems, where speed, lightness, transportability, and structural reliability are essential. Finally, we will examine hybrid structural systems, combinations of wood, steel, concrete, and glass, and discuss why contemporary architecture increasingly relies on multi-material integration rather than single-material systems. By the end of the lecture, you should be able to compare materials not only technically, but also environmentally and structurally. By the end of this lecture, you should be able to explain the environmental significance of recycling wood waste, identify structural versus non-structural applications of panel materials, compare particle board, MDF, OSB, plywood, and glulam in terms of strength and sustainability. Evaluate suitability in disaster response architecture. Analyze hybrid structural strategies. Critically assess material selection in terms of carbon footprint, durability, and structural behavior. Material selection today is no longer only about cost or availability. It is about environmental responsibility, structural safety, lifecycle performance, and resilience. Let us begin with recycling. Wood waste from furniture production, lumber mills, and demolition sites is often viewed as industrial waste. However, in sustainable construction systems, this waste becomes a valuable resource. Particle board production is a prime example. Wood chips, shavings, and fiber residues are collected and classified. They are dried to remove moisture, adjusted in size, mixed with resin binders, and pressed under high temperature and pressure. The result is a uniform board ready for finishing. This approach contributes to sustainability in three major ways. 1. It reduces the demand for virgin timber. 2. It minimizes landfill waste. 3. It improves raw material efficiency. However, sustainability must also consider binder content. Synthetic adhesives, especially formaldehyde-based resins, may negatively impact indoor air quality and recyclability. Therefore, sustainability evaluation must always include life cycle assessment, from raw material sourcing to end-of-life recyclability. Let us now examine particle board in more depth. Particle board is one of the earliest industrially engineered wood panel products. It is produced by compressing wood chips, shavings, and small particles together with synthetic resin binders under high temperature and pressure. Small diamond production structure and internal composition. The internal structure of particle board typically consists of 3 layers: a core layer made of larger wood particles, 2 outer layers made of finer particles. This layered system improves surface smoothness while keeping production costs low. However, because the particles are randomly distributed and not directionally aligned, the internal structural continuity is limited. Unlike plywood or OSB, particle board does not have directional reinforcement. Therefore, its mechanical behavior is isotropic but relatively weak. Small diamond mechanical properties. Particle board has low bending strength, limited tensile capacity, weak screw holding performance, low resistance to cyclic loading. These characteristics make it unsuitable for structural use. Under load, it tends to deform permanently, experience edge breakdown, lose structural integrity when exposed to moisture. In humid conditions, the board absorbs water, causing swelling and loss of mechanical properties. Once swollen, it does not return to its original strength. Small diamond sustainability perspective. From a sustainability standpoint, particle board has advantages. It recycles industrial waste. It reduces demand for virgin timber. It supports mass production efficiency. However, environmental performance depends heavily on the type of resin used. Formaldehyde emissions. End-of-life recyclability. Because it contains synthetic binders, it is difficult to recycle after use. Therefore, its sustainability is conditional, not absolute. Small diamond use in disaster context. In post-disaster housing, particle board should only be used in temporary interior furniture. Non-load bearing surfaces. It should not be used in structural walls, floor systems, exterior panels. In summary, particle board is economically efficient but structurally limited. Now let us examine OSB more technically. OSB is an engineered panel composed of long, thin wood strands arranged in oriented layers. The orientation is deliberate. Outer layers aligned in one direction. Inner core oriented perpendicular. This design mimics the structural logic of plywood but uses larger strands instead of veneers. Structural behavior. Because of its directional strand orientation, OSB exhibits high in-plane shear strength, improved bending capacity, strong fastener holding capacity, resistance to cyclic loading. In seismic engineering, OSB is commonly used as a shear wall diaphragm in timber framing systems. When lateral forces act on a building, OSB panels distribute forces evenly. Increase stiffness, improve structural stability. Its lightweight is a major advantage. Since seismic force equals mass times acceleration, reducing mass directly reduces seismic demand. Small diamond dynamic performance. OSB performs well under vibration and cyclic loads, which makes it particularly suitable for earthquake-prone regions. It also provides impact resistance and surface rigidity. Environmental considerations. OSB uses fast-growing wood species and wood waste strands, making it relatively resource efficient. Compared to concrete or steel, it has lower embodied energy, carbon storage potential. However, adhesives still affect recyclability. Small diamond use in disaster-resilient systems. In post-disaster construction, OSB is ideal for shear walls, floor decking, roof sheathing. It supports modular, prefabricated construction systems. Among panel materials, OSB represents a strong balance between cost, performance, and sustainability. Ecological, or blockboard, is a lightweight panel typically consisting of a core made of wood strips or particles with surface veneers. Its defining characteristic is low density, small diamond structural capacity. Ecological panels have limited bending strength, are not designed for load bearing, may deform under long-term loading. Because of the discontinuous core structure, stress transfer is not efficient. Small diamond advantages. Despite structural limitations, Ecological offers easy transportation, simple installation, reduced structural load, good thermal properties and interior use. It is frequently used in exhibition systems, interior partitions, temporary office modules. Small diamond disaster context. In temporary shelter systems, Ecological is suitable only for interior partition walls, light separation elements. It should not be used in structural frames. Exterior exposed surfaces. Moisture sensitivity remains a concern. Thus, Ecological is spatially flexible but structurally limited. MDF differs significantly from particle board in internal structure. It is made from wood fibers reduced to near dust form and bonded under high pressure. This results in a homogeneous internal structure. Small diamond surface and fabrication quality. MDF's greatest advantage is surface performance, smooth, uniform texture. Excellent for painting and lacquer. Ideal for CNC detailing. Clean edge machining. It allows precise interior architectural detailing. Small diamond structural limitations. Despite surface quality, MDF has low bending resistance, is extremely moisture sensitive, loses structural strength when wet, Because of fiber density, it absorbs water rapidly. In humid climates or disaster conditions involving flooding, MDF performance deteriorates quickly. Disaster management role. MDF can only be used for interior furniture, storage systems, non-structural partition panels. It cannot serve in load-bearing applications. From a sustainability perspective, frequent replacement due to moisture reduces its long-term environmental. Let us now examine plywood in greater structural and architectural depth. Plywood is an engineered wood panel composed of thin wood veneers bonded together with adjacent layers arranged perpendicular to one another. This cross-laminated configuration is the key to its mechanical strength. Unlike particle board or MDF, plywood benefits from directional grain reinforcement. Each layer resists movement in one direction, while the adjacent layer resists movement in the perpendicular direction. This significantly reduces dimensional instability such as warping, cracking, or splitting. Small diamond mechanical performance. Because of its layered cross-grain system, plywood exhibits high bending strength, improved tensile capacity, good shear resistance, enhanced dimensional stability, better fastener holding compared to particle board. The perpendicular layering interrupts crack propagation, which increases durability under stress. In structural applications, plywood is often used as floor sheathing, roof decking, shear wall panels, structural diaphragms. It behaves predictably under load, making it suitable for structural design calculations. Small diamond performance in seismic regions. Plywood is particularly important in earthquake-resistant timber systems. It performs well because it provides lateral stiffness. It distributes horizontal seismic forces. It improves energy dissipation. It adds minimal structural mass. Lightweight systems reduce seismic forces. Since earthquake force is proportional to mass, plywood-based structures benefit from reduced inertia. This makes plywood highly suitable for disaster-prone areas. Small diamond rapid construction and post-disaster use. One of plywood's greatest advantages is speed. It is manufactured in standardized sizes, easy to transport, simple to cut and assemble, compatible with prefabrication. In post-disaster scenarios, time is critical. Plywood enables temporary housing units, modular shelters, emergency response buildings. It balances structural performance, speed, and resource efficiency. From a sustainability perspective, plywood also stores carbon during its service life. Contrabass is a decorative surface panel consisting of a plywood base with a thin veneer surface. The structural behavior is controlled by plywood. Small diamond structural versus aesthetic role. The plywood base provides bending strength, dimensional stability. The veneer surface provides visual quality, wear resistance, architectural expression. It combines structural efficiency with aesthetic refinement. Modular and temporary use. In temporary structures, contrabass is effective for interior cladding, modular partition systems, lightweight assembly. It is easy to transport and assemble, making it suitable for rapid deployment. However, it remains a surface system, not a structural frame. Durability is directly linked to sustainability. A material that lasts longer reduces embodied carbon over time. Small diamond moisture sensitivity comparison. MDF and particle board. High swelling coefficient. Rapid strength loss. OSB and plywood. Moderate moisture resistance. Improved with surface treatments. Glulam. Requires protective detailing. Performs well when properly sealed. Design strategies for moisture protection. Architectural detailing is critical. Elevation above ground. Ventilation gaps. Protective coatings. Drainage detailing. Material selection alone is insufficient without proper detailing. Small diamond climate and disaster considerations. In flood-prone regions, moisture resistance becomes decisive. In seismic regions, lightweight materials reduce structural mass. In fire-prone areas, controlled charring behavior becomes important. Durability must be evaluated within environmental context. In this slide, we move from panel materials toward structural engineered timber, specifically glulam or glued laminated timber. Glulam is produced by bonding dried timber lamellas together with high-strength structural adhesives. The grain direction of each lamella is aligned parallel to the others. This alignment is extremely important because wood is anisotropic, meaning its strength properties vary depending on fiber direction. By controlling fiber orientation, glulam maximizes strength along the structural axis. One of the most important engineering advantages of glulam is defect control. Natural solid timber contains knots, cracks, density inconsistencies, and fiber deviations. During glulam production, defective segments are removed. Lamellas are strength graded. Moisture content is standardized. Layers are assembled strategically. This results in a material that is stronger and more predictable than solid timber. Another key advantage is its strength-to-weight ratio. Compared to reinforced concrete, glulam is significantly lighter while still capable of spanning 20 to 40 meters or more. This makes it ideal for sports halls, airports, cultural buildings, industrial halls, emergency assembly structures. Additionally, glulam allows curved geometries. Unlike steel or concrete, which require complex formwork or bending processes, glulam beams can be fabricated in curved shapes during production. This provides architectural flexibility while maintaining structural efficiency. From a sustainability perspective, glulam is renewable, recyclable, and acts as a carbon storage medium. During tree growth, carbon dioxide is absorbed from the atmosphere and stored in the wood fibers. When used structurally, this carbon remains sequestered for decades. Thus, glulam is not only a structural material, it is also a climate-responsive material. When comparing materials, particle board right pointing arrow low structural capacity. MDF right pointing arrow interior only use. OSB right pointing arrow good seismic suitability. Plywood right pointing arrow high structural reliability. Glulam right pointing arrow excellent structural and environmental performance. This matrix demonstrates that material selection must be performance-driven. Additionally, glulam allows curved geometries. Unlike steel or concrete, which require complex formwork or bending processes, glulam beams can be fabricated in curved shapes during production. This provides architectural flexibility while maintaining structural efficiency. From a sustainability perspective, glulam is renewable, recyclable, and acts as a carbon storage medium. During tree growth, carbon dioxide is absorbed from the atmosphere and stored in the wood fibers. When used structurally, this carbon remains sequestered for decades. Thus, glulam is not only a structural material, it is also a climate-responsive material. In this slide, we shift from structural systems to interior finishing materials, laminate materials. Laminate materials consist of multiple layers pressed together under high heat and pressure. Each layer serves a function: decorative surface layer, protective overlay, core paper or fiber layers, resin bonding system. Under thermosetting conditions, these layers become a unified, non-recyclable composite material. Laminate is widely used in furniture surfaces, cabinet doors, countertops, wall panels, flooring systems. Its primary advantages include high abrasion resistance, scratch resistance, stain resistance, impact resistance. Technological advancements in digital printing allow laminate surfaces to imitate natural materials such as wood, stone, marble, or concrete. However, from a sustainability perspective, laminates have limitations. Thermoset resins prevent recycling. Adhesive content increases embodied energy. End-of-life separation is difficult. Thus, laminate materials provide durability and aesthetic flexibility, but life cycle analysis must be considered carefully. Now let us shift from structural behavior to environmental evaluation. Life cycle assessment, or LCA, is a methodology used to measure the total environmental impact of a material throughout its entire lifespan. Small diamond LCA stages. When evaluating wood-based materials, we examine 1. Raw material extraction. 2. Production energy consumption. 3. Transportation. 4. Service life and durability. 5. End-of-life recyclability. 6. Carbon storage potential. This comprehensive approach allows us to compare materials objectively. Small diamond wood versus concrete versus steel. Engineered wood products generally show lower embodied energy than concrete, lower embodied carbon than steel. Carbon sequestration benefits. Trees absorb carbon dioxide during growth. When used in buildings, that carbon remains stored for decades. However, the environmental impact of adhesives and synthetic binders must be considered. These chemicals may reduce recyclability and introduce emissions. Therefore, the sustainability of wood-based materials is strong but conditional. Small diamond durability as a sustainability factor. A material with low embodied carbon but short lifespan may not be sustainable. Durability directly affects life cycle performance. If replacement frequency increases, total carbon footprint increases. Thus, sustainable design requires balancing initial embodied energy, long-term performance, maintenance requirements. Modern architecture increasingly favors hybrid systems. Reasons include single material limitations, diverse structural requirements, sustainability goals. Wood plus concrete plus steel combinations reduce total structural weight and improve seismic performance while balancing energy and comfort. Modern construction increasingly relies on hybrid systems rather than single material solutions. Why? Because no single material can optimize all structural, environmental, and spatial requirements simultaneously. Concrete performs excellently in compression but poorly in tension. Steel performs excellently in tension but requires corrosion protection. Wood is lightweight and sustainable but has span limitations. Hybrid systems strategically combine materials to compensate for weaknesses and maximize strengths. Hybrid systems improve structural efficiency, material optimization, seismic behavior, energy performance, architectural flexibility. This shift toward multi-material integration reflects a performance-driven design philosophy. Concrete cores combined with timber superstructures are increasingly common in mid-rise buildings. The reinforced concrete core provides vertical circulation support, lateral stiffness, fire-protected structural stability. The timber floors and beams provide reduced structural mass, faster assembly, improved indoor comfort. From an earthquake engineering perspective, this combination lowers seismic mass while maintaining stiffness. From an environmental perspective, substituting concrete floors with timber elements significantly reduces embodied carbon. This hybrid strategy balances structural safety and sustainability. To summarize, wood-based panels contribute to sustainability through recycling. Each panel type has distinct structural and environmental characteristics. OSB and plywood perform well in seismic systems. MDF and particle board are interior materials. Glulam offers long-span sustainable structural solutions. Hybrid systems enhance seismic performance and reduce carbon footprint. Sustainable architecture increasingly relies on multi-material integration.